All right, thanks everyone. I'm going to talk today about a paper called Carpooling and the Economics of Self-Driving Cars. This is joint work with Michael Schwarz, who is at Microsoft. And I only have 18 minutes, so I'm going to speak fast. I'm going to skip a bunch of things, but the slides are on my website along with the paper, so things that I skip, feel free to go and take a look at them. All right. So you've already seen this picture in the previous talk, and I'll show it again. This is what daily commuting looks like for hundreds of millions of people worldwide, both in rich countries, in New York, in LA, in San Francisco Bay Area, but also in developing countries as well, Mexico City, Jakarta, Delhi, they all look like this. And it's looked like that for many decades, and the question is, well, one question is it going to continue like that for the foreseeable future, or is there hope? And we think there is hope. And our starting point for this hope is that there are three emerging technologies that will transform transportation, and in particular will allow us to stop having things like that spoiling our lives. So one of them that's in the news, I'm not going to spend too much time talking about this, is self-driving cars. I do want to emphasize that when I say this, I don't mean this kind of science fiction-y things where they zip along at 500 miles per hour and don't stop at the intersections. I'm thinking about much more realistic case where you still have some mix of human-driven cars on the road, so they drive sort of like humans do, but they don't need an actual driver. So that's that. But there are two other technologies that are always often overlooked, but we think are at least as important for potentially relieving congestion. And one of them is frictionless time-dependent tolls, and the other one is convenient, efficient carpooling. And so the question in this paper is, what will a market powered by these three technologies look like, and how should it be designed and organized, right? And given that we don't have a dictator, we don't want to have a dictator who tells everyone what to do and when to leave, when to come back from work. How can governments best facilitate solving this, relying on these three technologies? And the structure of my talk is going to be a little bit unusual. I'll first motivate why we're talking about this as new technologies. Then I'm going to talk about interactions among them, why it's important to look at them together rather than separately. And only after that will I launch into a mathematical model, and I'll actually tell you some math. All right, so first let me talk about tolls. Why am I talking about tolls as an emerging future technology? And here is why. So this is a photo of the Bay Bridge in San Francisco, and this is going to San Francisco from East Bay. And as you can obviously see from the picture, it's incredibly expensive to install one of those things. So we only have toll collection tools in very few locations. And so, for example, if you wanted to introduce time-varying congestion relieving tolls in the San Francisco Bay Area, you would be able to do it for the morning commute, right, for people going from East Bay to San Francisco, but you wouldn't be able to do it in the opposite direction because on the Bay Bridge, tolls are only in one direction, right? So from the start, you're severely limited right now. Fortunately, this is changing very, very soon. The technology that's coming is tolls based on GPS, or some people think it's going to be more based on cameras taking photos of license plates and then just sending you bills. From our point of view, it doesn't matter which it is. What's important is that obviously it's very hard to get this technology off the ground. The fixed cost is huge to get it started, but once you have it, the marginal cost of actually adding these tolls to each little segment of a road is essentially zero, right? So that would really allow you to have frictionless time-dependent tolls in the way that right now we do not have this technology, even though we do have kind of very crude form of tolls. Another technology that we say is an emerging technology is carpooling. And again, your reaction is, why do I say this is an emerging technology? People have been carpooling for whoever knows how long. All you need to do is just put another person in the car. So a more accurate description of what we're talking about would be a carpooling matching technology, right? The technology for finding carpooling partners, for identifying people who you will carpool with. And those of you who tried carpooling with strangers, I'm not talking about carpooling with your family members, know that it's just a major hassle, right? Occasionally, you're able to find someone who is a regular carpooling partner for you, but even then, they have a doctor's appointment, or their plans change. So empirically, even though governments worldwide have been trying to convince people to carpool for many decades, all the efforts failed. So at most, around 10% of people carpool, and on any given day. And of that 10%, the vast majority are family members traveling together. So like genuine strangers carpooling together is basically almost non-existent. So what's changing now is that there are all kinds of apps, and I'm not going to go into details about their approaches, that are trying to reduce the costs of carpooling and facilitating people driving together. And I want to emphasize, and I'll come back to this point later, is all these apps are for sort of casual carpoolers. This is not for professional drivers. Right? What's going to be very important for us is people carpooling together who are both going from A to B because they want to go from A to B. There is no professional driver there. Having professional drivers will mix things up. I'll come back to this later in the talk. All right. So as I mentioned, it's important to talk about those three technologies together. And in the paper, we actually spent many pages going through all the different reasons for that. I don't have time to do that. I'll just give you a brief highlight of kind of the most important ones. So the first complementarity is between autonomous transportation and carpooling. And we have a lot of logistical reasons why they become attractive together rather than each separately. But the big picture view I want you to think about is that if you think about public transportation, one of the major costs of public transportation is the human driver, the time of the person driving the vehicle, which is why the way public transportation works right now is almost all of it happens in large vehicles that carry a lot of passengers, because that allows you to split the cost of the one driver among many passengers. That in turn forces these vehicles to be relatively inconvenient. They have predetermined fixed paths. They need to make a lot of stops, so that kind of really damages the quality of the surface. Once you take that one cost out of the equation, suddenly it becomes feasible to have kind of public transportation of all the different sizes, and more generally, the boundary between solo driving and public transportation, which is very sharp now, becomes blurred, right? So it's entirely possible a person will carpool with will ride together with 3 other people on the way to work and ride solo on the way back. Right? So the line becomes generally blurred. And as I said, we have a lot more very specific and logistical reasons in the paper. All right. Another important complementarity is between autonomous transportation and road pricing. Okay, why? What's the connection? And again, we have a bunch of logistical reasons, just technologically easier to do road pricing once you have self-driving cars, because they already know where they are. But more interestingly, from the economics point of view, is the equilibrium effect. And here it is. So when you think about self-driving cars, your image is, oh, it's wonderful when I'm stuck in traffic. Instead of getting mad and sort of wasting my time, I can read a book, I can sleep, I can watch TV. It's wonderful. Well, it's wonderful until you start thinking about the equilibrium effect from this, which is if you know that getting stuck in traffic is not so bad, well, then you no longer have a strong incentive to avoid peak hours, right? So if you go during peak hours, you will spend 10 minutes more in traffic than if you try to beat traffic and depart 2 hours earlier, but you don't care, you're just going to read a book, which is fine for you. But if everyone starts doing that, overall congestion just gets much worse, right? If everyone says, oh, driving in peak hours is not that bad, we're not the only ones who recognize that. There is a quote from Elon Musk, who's obviously a pro-self-driving car executive, warning about exactly the same danger. And in that case, having road pricing or something like that becomes even more important. All right, the last complementarity that I want to talk about before I shift to math is probably the most important one for a couple of reasons. One is it's actually important even if self-driving cars don't materialize. Even if 10 years from now we look back and say, oh, it was all hype, it's too hard, we can't do it. Although our colleagues, in other rooms are probably, hopefully, coming up with all kinds of algorithms for this. But if that doesn't happen, this particular observation is still going to be incredibly important. And that is the complementarity between carpooling and road pricing. Okay? And there are obviously tons of papers in economics, OR, other sciences talking about road pricing, but they overlook carpooling. They usually think about solo driving. Similarly, there are lots of papers thinking about carpooling. They tend to overlook road pricing. And our observation, which is ex post sort of obvious, is that looking at them together is incredibly important. So let me give you a very simple example based on the canonical bottleneck model of Vickrey. In the bottleneck model of Vickrey, there is a road segment. People are going from A to B. There is a capacity that this road segment has. And as long as you're under that capacity, everything is fine. Think of this as take people 0 seconds to go from A to B. Once there is more demand than supply, sort of like in the fluid model we saw earlier, there is a backlog. They start, the queue starts forming, and all kinds of bad things start happening. Okay, so in that world, suppose the number of people who want to go through that segment is twice the capacity of the road. Okay, so twice as many people. Obviously things are bad. You get congestion, all these terrible things, the picture I showed you. And suppose in this world, carpooling becomes super convenient, right? All these apps that I kind of flashed in front of you become wonderful. You're still better off going on your own rather than carpooling with other people. So they're not quite that magical, but you're almost indifferent, right? There is a small delta by which you prefer driving solo to carpooling. Well, guess what? That doesn't do anyone any good, right? Because individually, you're still better off driving on your own. So everyone else does the same thing. You wish everyone else was carpooling. It would be very cheap for them, but hey, that's life. Okay, so carpooling by itself has sort of no bite whatsoever. Okay, so now let's think about the other part. Think about road pricing, right? Those of you who are economists here, like, well, we know what to do. Back to Pigou and like all those other great economists, we should just set correct tolls. Okay, and you come here and you figure out the tolls, and in fact, that's exactly what this Vickrey paper, which is now exactly 50 years old, that's exactly what he did. And this is, by the way, it's a beautiful paper. If you haven't seen it, highly recommend it. And he characterizes what the optimal tolls look like, and they look exactly what you would expect. They're 0 off peak, then they gradually get to some high level, then they go down, they get rid of congestion. Everything is wonderful until you start thinking. And to Vickrey's credit, he did. So he actually talked about problems here. And here is the major problem. So imagine drivers are homogeneous in the sense of how much they value time. Okay? But they're different in terms of their optimal arrival times, what time they want to get to work. There is a distribution, but they all value time $1 per minute. Then, when you impose these optimal tariffs, the drivers are exactly as well off as they were before. The drivers do not get better off. What happens, and once you think about it has to be this way, what happens is the tolls are equal to the amount of time they were wasting in traffic beforehand. So for each individual driver, they're not better off. So the only change is that what they used to waste in terms of being stuck in traffic is now collected by the government. Now, if you live in a country where the government is wonderful and does the right thing with the revenue and somehow has a magical way of doing this in a way that benefits all the drivers, then that maybe it's not a problem. But in most places, that's actually a major concern. And if you're a driver, that you basically have to trust the government to not just do the right thing with the money, but also to benefit you personally. So things face massive political opposition. Things get even worse if you have heterogeneous values per time, because now you basically just price out all the poor people and you get into Lexus lanes, which is a common derogatory term for this, and things collapse. And again, this is something you see time and time again when tolls are proposed. And the last observation I'll make is that there are two inefficiencies in the Vickrey model. One is just this, people are backing up and queuing on the road. The other one is the arrival times when they get to work are not the ones they want. And that is not fixed even with tolls. Okay, so tolls are not nearly as good as you may have thought they were before you stepped into this room. So now suppose you have both of those technologies together. Okay, you have carpooling and you have road pricing, and you set tolls just above delta. Well, so now that's when all the magic happens. All the drivers are better off because you just doubled the capacity of the road. Okay, and that's why it's so important to think about these two things together. All right, I have less than 5 minutes, so let me quickly just tell you what the model looks like and what the main results are. So in the model, we have a finite set of riders, 1 through m. We have a finite set of road segments, 1 through s, and each road segment specifies the physical location of the road and the specific time interval, so tolls are time dependent. Each road segment s has an integer capacity qs, just like in Vickrey, how many cars can pass through this segment during that time. And a trip is a feasible combination of one or more riders and one or more road segments, right? So feasible just means that physically makes sense. If this rider needs to go from here to here, these are the segments they need. And just combinatorially, there is a finite number t, that could be very large, of possible trips t1 through t. And each trip t has a physical cost c of t, think of this as gas and wear and tear on the car, associated with it. All right? Each rider has a valuation for every trip that involves him. Money enters utility quasi-linearly, the way you would expect. Each rider has an outside option, not very important. What's important is there is a notion of assignment, which tells us what trips get formed, right? Who is going in which road segments with whom. And an assignment is feasible if it physically makes sense, if no road is used more than its capacity. The social surplus of an assignment is just the sum of people's utilities minus all the physical costs, the way you would expect. And now what we really wanted to answer, what we really want to think about, how can you get to good assignments with kind of minimal government intervention? Like, do you need some really complicated price systems, or what do you need? Turns out, and I'll show you in a couple of slides, all you need are two sets of prices. One is a price vector, non-negative price vector P, that specifies the price paid by each rider M, right? How much the rider needs to pay for the trip they get. And the other one is a non-negative vector R that specifies tolls imposed by the regulator on each road segment at each moment in time. But notice that R doesn't specify how many people are in the car. It doesn't specify prices for whole trips, right? So you don't need super complicated prices. All you need is just prices per road segment, and then for the whole trip is just the sum. And an outcome is a physical plan, who goes where with whom, and this pair of prices that will support this outcome. All right, so what do we want an outcome to satisfy? We say the outcome is feasible if the assignment A in it is feasible, right? Just physical feasibility, not very interesting. It's budget balanced if the sum of prices paid by the riders is sufficient to cover all the expenses. Okay, that's kind of self-explanatory. And the last two are substantive. First, we say that an outcome is stable if riders on their own can't organize a trip that makes all of them involved in this trip better off than they were under APR, just like in standard matching literature, which sounds like by itself it might be enough, but not quite. So suppose you have those first three characteristics, and consider an assignment where everyone stays home, an outcome where everyone stays home, and all the prices for road segments are infinite. That's going to be a feasible, budget balanced, and it's going to be stable because no one can organize a better trip given the high prices. Okay? So the problem with this outcome is prices are too high, so we impose the last condition that we call market clearing. We say that an outcome is market clearing if you can only charge positive prices for segments that are at capacity. Whenever a segment is under capacity, price has to be equal to 0. Okay? And our first main result, and the only one I have time to tell you about, is that if an outcome APR is feasible, stable, budget balanced, and market clearing, then assignment A has the highest possible social surplus among all the feasible outcomes. So to translate it back from math to plain English, if you can set prices in such a way that you get such an outcome, then this is the best possible thing you can do. You don't need to have other additional policies like giving people discounts when multiple people are in the same car, having more complicated prices that are for the entire set of segments. All right? Thank you.